Lesson 75, Integration by Trig Substitution. In this lesson, we will look at the next type of integration technique called trig substitution, which is very useful for simplifying any integrand that contains a quadratic radical expression in the denominator. Before we learn how to use trig substitution, I just want you to do a warm-up. Take a look at the expressions given below. U equals arc sine x over a, u equals to arc secant x over a, and u equals to arc tan x over a. Use this information to label all three sides of each one of these right triangles. Pause the video and come back to this when you're done. Okay, so assuming that you have tried these questions, I'm going to start labeling these diagrams. So I will let the bottom angle u. Arc sine is opposite over hypotenuse when I look at x over a. So x is here, a is here, making a squared minus x squared square root at the bottom. The second triangle, if I let u to be here, secant is hypotenuse over adjacent, so x over a like that, making the opposite side from u, x squared minus a squared square root. Last triangle, we have arc tan of u, or tangent of u, is x over a, making the hypotenuse x squared plus a squared square root. Okay? So what does this mean to us? Well, it means that when I see square root of a squared minus x squared in my integrand, in the denominator of an integrand, I can set a sine u to equal to x. If I see square root of x squared minus a squared in the denominator of the integrand, I can let x be a secant u. And if I see the square root of x squared plus a squared, then I will let a tan u equals to x. The reason may not be apparent yet, but let's take a look at the next two examples for this to become a little more clear. Example 1. Find dx over 9 minus x squared to the power of 3 over 2. In order for us to use trig substitution, let's rewrite this as the dx over square root of 9 minus x squared to the power of 3. This way, we can compare it to the chart that we have earlier. Notice how we have the format of square root of a squared minus x squared. This suggests that our substitution should be a, which in this case is 3, sine u equals to x. Let's use this to label the diagram. So if this is angle u, then opposite is x, hypotenuse is 3, making the adjacent side 9 minus x squared. And here you see how this expression matches with what we have in our integrand. Well, let's try to differentiate 3 sine u x to find an equivalent expression for dx. So here we have 3 cosine u du equals to dx. So I know right away that dx will be replaced by the left side here, okay? Do we have everything that we really need? Well, just to clarify, because our question, the integrand, has the cubic of square root of 9 minus x squared. What does that look like in terms of u? Okay? Well, this is the adjacent side, correct? Another way to express the adjacent side in terms of the angle u is to use 3 cosine u. So now I think we are ready to do the actual substitution. Here now we have dx is replaced by 3 cosine u du over the square root of 9 minus x squared is replaced by 3 cosine u, but this needs to be cubed. All right. Let's simplify this expression. I have 3 over 3 cubed. So that means I have 1 over 3 squared, 1 over 9, the integral of cos u over cos cubed u. That means I have 1 over cos squared u du. But 1 over cos squared can actually be written as secant squared u. And this is good news because I know the integral of secant squared u is tan u plus c. We're not done yet because our original question was expressed in terms of x. Now we need to find an expression to replace tan u that is in terms of x. Okay, so let's go back to our substitution section. Now the next step is, what is tan u? Well, tangent is opposite over adjacent. Using my triangle, this is what I get. Therefore, my final answer will involve multiplying 1 over 9 by x over 9 minus x squared plus c, or it is x over 9 root 9 minus x squared plus c. So we'll take a little while to get used to this. We'll do this slowly again in question 2. Okay, so here we have this integral of dx over x squared square root of x squared minus 4. Now this time the square root format is x squared minus a squared. Okay, let's take a look at the chart. It matches with the second substitution. We're going to let a secant u to be x. Okay, we're going to let a, which is 2, right, square root of 4, secant u is x. We'll use this substitution. We can mark this on our diagram. Secant u is x over 2. So x is hypotenuse, 2 is adjacent, making opposite x squared minus 2 squared, which is 4. And there is your expression. Okay. Taking the derivative of our last statement, I have 2 secant u tan u du equals to dx. Okay. And let's see what else we need. We have that square root expression, right, in our question. What does this look like in terms of u? This is the opposite side. So if this is the opposite side, I can express this as adjacent side multiplied by tan u. And I also see an x squared in my original integrand. What is x squared? Well, I can make use of the previous line. If I square both sides, I get 4 tan squared u and then plus 4. But this is 4 secant squared u, right? If you factor out 4, you get tan squared u plus 1, which is really secant squared. Okay, so these are all useful to me. Let's make the substitution. We're going to replace dx by the second line here. This one. Don't want it to make it look like a negative sign. 2 secant u tan u du. X squared is 4 secant square u, and square root of x squared minus 4 is 2 tan u, like that. Let's simplify. 2 and 2 gone, 10 and 10 gone, secant, one of the secants gone. I have 1 over 4 square root of, now I have 1 over secant u, which really is cosine. Look how easy now it is to integrate cosine u. And this is why trig substitution is very useful. Okay, The integral of cosine u is sine u plus c. So from what we have done in the first example, now it's the time to write sine u in terms of x again. Okay? Now sine u is the square root of x squared minus 4 over x. Therefore, my final answer will be 1 over 4 times that.